Properties of gases, especially air.
So what are the properties of gases? So gases do not possess any definite volume or shape. They totally fill all the space accessible to them. The characteristic or properties of gases to fill the available volume within a container is the result of the freedom that gas particles have to move everywhere in the accessible space. This autonomy of movements of gaseous molecules is because of the very weak binding forces amidst molecules. In other words, their intermolecular forces are very weak. Because of this, the molecules of a gas are in a continuous motion and are related to high velocity and therefore high kinetic energy. The properties of gases: number 1, compressibility; number 2, expansibility; number 3, diffusibility; number 4, low density; and number 5, exertion of pressure.
Number 1. Compressibility. Particles of gas have huge intermolecular spaces in the midst of them. By the exertion of pressure, much of this space can be diminished, and the particles are brought closer. Thus, the volume of gas can be hugely reduced. This is termed as compressing the gas, and this is shown in the figure below, where gas is being compressed.
Additional information about the compressibility of gases. So gases can expand to fill its container, unlike solids or liquids. The reverse is also true. They are easily compressed or squeezed into a small volume. Compressibility is a measure of how much the volume of matter decreases under pressure. Number 2, expansibility. When pressure is exerted on gas, it contracts. On the other hand, when pressure is freed, the gas expands. When the temperature is augmented, the constituent particles gain more energy, travel faster and move away from each other. Consequently, the intermolecular pull becomes less prominent. The gas volume increases. Number 3, diffusibility. The molecules of the gas are in perpetual motion at very high velocity. There is a huge amount of intermolecular space amid the molecules. When two gases are mixed, particles of one gas can effortlessly pass through the intermolecular space of the other gas. As an outcome, both the gases get completely and consistently mixed. Thus, a mixture of gases at all times remains homogeneous. So, diffusion describes the mixing of gases. The rate of diffusion is the rate of gas mixing. Molecules move from areas of high concentration to low concentration. So, number 4, low density. So since gases have large intermolecular spaces, they have very large volumes when compared to their mass. Therefore, they have less densities. If 1 ml of water at 39.2 Fahrenheit is transformed into steam at 212 Fahrenheit and 1 atmosphere pressure, it will occupy a volume of 1,700 ml. Number 5, exertion of pressure. Solids exert pressure only in the downward direction. Liquids apply pressure downward as well as the sides. But gases apply pressure in all directions. A good example is a balloon. This pressure is because of the bombardment of the particles against the walls of the vessel, and this is clearly shown in the figure below. So the atmosphere is all around us, an ocean of gases mixed together, and it is composed of nitrogen N2, which is 78%, oxygen O2, which is 21%, argon Ar, which is 1%, carbon dioxide CO2, which is 0.04%, water vapor H2O, which is 0.1%, and other trace amounts of He, Ne, Rn, SO2, CH4, NX, OX, and more. Variables that describes gases. There are four variables used to describe gases. Number one is pressure, number two, volume, number three, temperature, and number four, amount. So the symbol for pressure is P, volume is V, temperature is T, and amount is small letter n.
Units of pressure. The standard unit for pressure is atmosphere or ATM. Other units include kPa is equal to kilopascal, mmHg is equal to millimeter of mercury, torr is equal to torricelli, psi is equal to pounds per square inch.
Units of volume. The standard unit for volume is the liter or L. There are 1000 ml in 1 liter. Units of temperature. The standard unit for temperature is Kelvin or K. Other units include degrees Celsius C, degrees Fahrenheit F. Absolute zero. The theoretical temperature at which all kinetic motion completely stops, equal to 0 Kelvin or negative 273 degrees Celsius. Conversions. Kelvin is equal to degrees Celsius plus 273. Degrees Celsius is equal to Kelvin minus 273. Kinetic molecular theory. The theory states that tiny particles in all forms matter are in constant motion. This theory is used to explain the behavior common among gases. There are three basic assumptions of the KMT as it applies to gases. Three basic assumptions of the kinetic theory as it applies to gases. Number one, a gas is composed of small particles that have mass, usually molecules or atoms. They have insignificant volume, relatively far apart from each other, no attraction or repulsion between particles. Number two, particles in a gas move rapidly in constant random motion, move in straight paths, changing direction only when colliding with one another or other objects. Average speed of O2 in air at 20 degrees Celsius is an amazing 1,700 km per hour. Number three, collisions are perfectly elastic, meaning kinetic energy is transferred without loss from one particle to another. The total kinetic energy remains constant. So we all know that atmospheric pressure changes with varying altitude, and as we go up higher, the pressure decreases. It is because as the altitude increases, the air gets thinner, and that's when we notice pressure drop. This explains why mountain climbers bring oxygen cylinders, especially if they are climbing the world's highest mountains like Mount Everest, because it's difficult to breathe there due to low air pressure and low oxygen. While as if we are at sea level, pressure is in the normal condition, and we can observe the pressure changes and measure it with a barometer, as seen in the figure. So this is an early barometer where the normal pressure due to the atmosphere at sea level can support a column of mercury that is 760 millimeter high. So the first device for measuring atmospheric pressure was developed by Evangelista Torricelli during the 17th century. The device was called a barometer. Baro is equal to weight, meter is equal to measure. And this is him. This is the image of Torricelli.
Charles law. And the formula for Charles law is V1 over T1 is equal to V2 over T2. And Charles law states that as the temperature of a gas increases, the volumes increases proportionally, provided that the pressure and chemical amount of gas remain constant. And this needs to be done in Kelvin. So temperature K or Kelvin is equal to temperature C or degrees Celsius plus 273. Boyle's law, and the formula for Boyle's law is P1V1 is equal to P2V2. And Boyle's law states that as the pressure on a gas increases, the volume of the gas decreases proportionally, provided that the temperature and chemical amount of gas remain constant. The ideal gas law. So, ideal gas law is based on how gases will interact within a system. Hypothetically, all gas follow this law, and this need to make few assumptions from the real world. Ideal gas law. So if we recall Boyle's law, V is proportional to 1 over P. In Charles' law, V is proportional to T. And in Avogadro's theory, V is proportional to N. Can we combine all this to give V is proportional to 1 over P times T times N? Or V is equal to R times 1 over P times T times N, where R is constant. Then PV is equal to nRT, where R is the universal gas constant. Combined gas law. So in Boyle's law, PV is equal to constant. In Charles' law, V over T is equal to constant. So we are able to combine both to give P times V over T is equal to constant. So physical characteristics of gases. So gases assume the volume and shape of their containers. Gases are the most compressible state of matter. Gases will mix evenly and completely when confined to the same container. Gases have much lower densities than liquids and solids. Gases have mass. So gases seem to be weightless, but they are classified as matter, which means they have mass. The density of a gas, the mass per unit of volume, is much less than the density of a liquid or solid. However, it's this very low density that allows us to be able to walk through the room without concerning ourselves with air resistance. Since it is so easy to swim across the room, we don't put much though into the mass of a gas. Really, it is only noticeable if we have a large collection of gas in a container. So that's all sir for this topic, and I hope you like the video, and thank you for watching.